Good morning, everybody. In the previous videos, I already discussed about Coulomb's theorem, Gauss theorem, electric potential, electric field, etc. Now, I am going to discuss about electric potential energy. And please watch my video and please like the video and subscribe my channel. Please watch the video. Today's topic is electric potential energy. We already discussed about electric potential at a point inside an electric field. Let us consider this is an electric field having electric field strength E. P is a point inside the electric field and V be the electric potential at the point P. Now, to bring the positive charge from infinity to that point P against the force is equal to the electric potential energy at that point P. So let V be the potential, electric potential, V be the electric potential at a point P. A charge plus Q is brought from infinity to the point P. The work done is equal to the potential energy is equal to the potential energy stored at the point P. That is potential energy PE is equal to U is equal to Q into V. Now we consider another charge plus Q at a point O, and PB a point from the distance r, at the distance r from the point O. Now plus Q charge is brought from infinity to the point. We know electric potential at the point P is V is equal to 1 by 4 pi epsilon 0 Q by R. This is the electric potential produced at the point P due to the point charge plus Q. Where V is the electric potential produced at the point P due to the point charge plus Q or Q. Point charge plus Q. Therefore, potential energy at the point P is U is equal to 1 by 4 pi epsilon 0 small q capital Q by R. Now we have to find out the potential energy stored in a charge system. Let us consider A, B, C is a triangle. Length of the side AB is equal to R, 1 in the suffix 1, and the length of the side BC is R, 2, 3. Length of the side AC is R, 3, 1. Initially, the system is neutral line. After that, a point charge Q1 is brought from infinity at that point Q. At that point A, that is, a charge Q1 is brought from infinity to the point A. This charge Q1 does not experience any electrostatic force, either repulsion or attraction. That's why there is no work done to bring the charge q1 from infinity to that point A. Therefore, the work done to bring charge plus q1 from infinity to the point A is W1 is equal to 0. Now we bring another charge q2 from infinity to the point B. Here q2 experiences a repulsive force produced by q1. Okay, therefore the work done to bring the charge q2 from infinity to the point B is how much? W2 is equal to 1 by 4 pi epsilon 0 q1 q2 by r1, since r12 is the distance between A and B. Now we bring another charge q3 from infinity to the point QC. Now Q3 experiences the resultant force produces due to Q1 charge and Q2 charge. Therefore, the work done to bring the charge Q3 from infinity to the point C is W3 is equal to the Q3 into Q2, the distance between BC is R23. Therefore, the work done is equal to 1 by 4 pi epsilon 0 Q2 Q3 by R23. This work done is against the force produced by Q2 charge plus 1 by 4 pi epsilon 0 Q3 into Q1 by R32. This work done is against the force produced by charge Q1. Therefore, the total work done to form the charge system is equal to W, and which is equal to the potential energy stored in the system. Therefore, total work done W is equal to W1 plus W2 plus W3. Okay, total work done W is equal to W1 plus W2 plus W3. Therefore, potential energy stored in the system is U is equal to W1 plus W2 plus W3 is equal to 1 by 4 by epsilon 0 Q1 Q2 by R1 plus Q2 Q3 by R2 3 plus Q3 Q1 by R3 1. In general, for the system which is formed by n number of charge, in general, U is equal to 1 by 4 by epsilon 0 double summation I is equal to 1 to n, j is equal to 1 to n, qy qj by rij. Here I not equal to j. For the n number of three number of the charges q1 q2 by r12 plus q2 q3 by r23 plus q3 q1 by r3. Here, since here q1 q2 is equal to q2 q3 and r12 is equal to r21, since from the summation we get the result twice, that's why we divide this result by 2. This is the final expression of electric potential of a system. And now we derive the work done to rotate an electric dipole inside an uniform electric field. This is an uniform electric field having electric field strength E. An electric dipole is placed which makes an angle theta with the direction of the electric field. We know that torque acts on the electric dipole is tau is equal to QE sin theta. Torque acts on the electric dipole placed inside an uniform electric field electric field having field strength E is equal to tau is equal to PE sin theta. Okay, PE sin theta, where P is the electric dipole moment and theta is the angle between P vector and E vector. Now, this electric dipole is slightly rotated or angularly displaced by a small angle d theta. Now, this dipole is slightly rotate by a very small angle d theta. Therefore, the work done dW is equal to tau into d theta. Therefore, potential energy stored in the dipole when it is displaced from the angle theta 1 to theta 2 is U. Therefore, U is equal to integration theta 1 to theta 2 tau d theta. This is equal to P integration of theta 1 to theta 2 sin theta d theta. This is equal to integration of sin theta is equal to minus of cos theta, theta 2 to theta 1. This is equal to P E cos theta 1 minus theta 2. Since we know tau is equal to PE sin theta and PE is constant. Okay, this is the expression of electric potential energy stored in an electric diode. Now we are going to find out the relation between change of potential energy and change of kinetic energy of a charged particle. Let Q be a plus Q be a small U positive charge having uniform velocity v. It moves towards a positive charge plate which repels the plus Q charge. After some time, its velocity becomes v2. Let v1 and v2 be the initial and final velocity of a charged particle having charge Q and mass m. The change in electric potential is capital P. Therefore, gaining potential energy PE is equal to loss in kinetic energy. Loss in kinetic energy. Therefore, Q into V is equal to half m small v2 square minus small v1 square. This is the relation between potential energy and kinetic energy in an electric field. From this relation, we can also define electrovolt. Electrovolt or electron volt is an U is a unit of energy. Okay. Let us consider an electron moves in an electric field against the force. Now, the work done to cover a point from A to B having potential difference 1 volt is equal to 1 electron volt. Let AB be the 2 points having potential difference is equal to 1 volt. An electron minus Q moves against the force. Then the work done is equal to 1 electron volt. Therefore, 1 electrovolt is equal to charge of an electron into 1 volt. Therefore, 1 electrovolt is equal to charge of an electron 1.6 into 10 to the power minus 19 coulomb into 1 volt. 1 coulomb into 1 volt. Therefore, 1 electrovolt is equal to 1.6 into 10 to the power minus 19 joule. This is the relation between joule and electron volt. And we can also know that a mass can be changed into energy. Therefore, 1 AMU, that means 1 atomic mass unit, can also be written in 1 electron volt.